and gang, thanks a lot, appreciate it. We talked about total body clearance, which I just abbreviated as clearance total. And a couple of things I didn't mention. We said that clearance total was equal to V times KEL. Okay. Let's write the model up here. So the model is very helpful. KEL. So, remember we said that since KEL in this model is equal to KU plus KM, M is pretty shallow, KM, then this is the same thing as V times KU plus KM. Okay, right? Because KEL is the same as KU plus KM. So we can break this out. V times KU is equal to what we refer to as renal clearance. CL sub R, renal clearance. Through that pathway. You've heard of the concept of renal clearance before, I'm sure in class, you might not calculate it, but renal clearance. That's V times KU, and V times KM, we're just going to call it metabolic clearance or hepatic clearance. Since most of metabolism is occurring in the liver, we just call it hepatic clearance. Okay. So therefore, bang, 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 total clearance is the same thing as renal clearance plus hepatic clearance in this model, where we're only showing these two routes of elimination. Okay. Can renal clearance exceed total clearance? Based on this equation, this concept?
No.
No. Can hepatic clearance exceed total clearance? Let me ask you another question. When will hepatic clearance be the same as total clearance, based on that model? When will hepatic clearance, multiple choice question on your next exam, when will hepatic clearance be the same as total clearance?
When there is no clearance.
When there is no renal clearance, exactly right. So none of the drugs you treated over here, when you get your scratch paper or dry erase board or whatever we're gonna be using on Monday, draw a little representation of the model or whatever case, because it's gonna help you to answer. I'm telling you straight, or you just have it firmly in your vision or head or whatever, because the model helps you to answer a lot of questions. Hold on for a moment, because you're younger than me and I won't forget. When will renal clearance be the same as total clearance? But there's no hepatic clearance. So if there's no hepatic clearance, if this pathway is blocked, then KU is equal to KEL, and if hepatic clearance is blocked, then total clearance is equal to renal clearance. If there is no renal clearance, in other words, none of the drug is, remember we said AU is the amount of the cumulative amount of drug of the free drug. So none of the unmetabolized apparent drug is free over here in this form, which we'll talk a little bit about urinary excretion. Bang, bang, bang. I think either tomorrow or Friday at the latest. I want to try to get ahead of it so that next week in laboratory, we can maybe work on a urinary excretion problem or something like that. Don't forget now, don't break my heart this week. On Friday, I've already assigned you a laboratory assignment. I give you those extra problems. Don't come to the laboratory and you haven't even worked on it. I assigned you some extra problems from chapter 4, remember? One compartment. So total clearance in this model is also equal to renal clearance plus hepatic clearance. So I wanted to, I didn't mention that the other day, where renal clearance is V times KU. There's some other ways to calculate renal clearance too, but I'm just going to leave it at that. Hepatic clearance is V times KM, okay? So that's one thing I wanted to tidy up a little bit. And we also said that we can calculate clearance as equal to V times KEL. That's equal to clearance. That was one way. We said this was model dependent or model independent. V times KEL.
Independent.
No, it's model dependent. No, the V times KEL is for this model. But we said there was another way of calculating clearance. We said the clearance could also be equal to the dose, A0, divided by the area under the curve from 0 to infinity. Okay, so we covered that too. And we talked about two ways of calculating area under the curve from 0 to infinity. And then I just want to get you started on an example from the textbook in chapter 4, and then we'll be through. So we said we can calculate the area under the curve. Now this is the area under the plasma concentration time curve. Okay. We said that one way, at least for this model, is equal area under the curve from 0 to infinity is equal to C0 divided by KL, did we not? So that's one way to do it. We know how to get C0 for the model, and we know how to get KL. So that's one way. And the second way, we say we can get area under the curve from 0 to infinity by the method of trapezoid. I'm going to say trapezoid. When I was in school, we called it trapezoid rule. Trapezoidal rule or method of trapezoids or whatever the case may be. Okay. And I briefly ran through that. I think that was the last thing I did on Friday. So I just want to just revisit that briefly and then put some real numbers in there from problem number 2 in chapter 4 that we worked on for last week in laboratory, just to show you how you would calculate a couple of those trapezoids. And then you can just do the rest of them. Because what I want you to do also in preparation for laboratory is in problem number 2. That was the only one that had some graphical data in chapter 4. Remember, we spent most time. I want you to go back and I want you to calculate. I don't know if the book actually calculated the clearance. I don't think we did. Go back and calculate the clearance for that problem. Well, you already know V and KL because we calculated those in lab. Go back and calculate the clearance. And calculate the clearance using both of these methods right here. For problem number 2. Chapter 4, in chapter 4. Am I making myself clear? Problem number 2 that we spend most of the time on in the laboratory, the textbook didn't have you calculate clearance for that problem and area. I'm asking you to go back and do that. So next Monday, if you call upon to do that, you say, it's a walk in the park, okay? So this trapezoidal method of trapezoids, I kind of flew through it on Friday because we're out of time. So let's just revisit that for a moment. Method of trapezoids. Method of trapezoids. For the area under the curve from 0 to infinity. So, a trapezoid, if you recall from pre-algebra or whatever, it's just this geometric figure with these uneven parallel sides we call H1 and H2, and it's got a width. And the area of this trapezoid is equal to H1 plus H2 divided by the width times 2. Now, I'm sorry, I didn't do that right. That's just as wrong as the day is long. It's H1 plus H2 divided by 2. Divided by 2 times the width. That's the area. So that's the area for this trapezoid. Area. So when we have our blood concentration time profile, okay, instead of, we okay with this? So when we look at our trapezoids for the area under the curve, okay, the heights are in concentrations, amen? The heights are in concentration and the widths are in time units, right? So for our area, so when we're doing it for the area under the curve, each trapezoid, I'm gonna call this C1 and C2, and this is the time, okay? So the area for each one of those trapezoids, the area is equal to C1 plus C2. In other words, these concentration right here. That's C2. This is C1 right here. C1. C1 plus C2 divided by T. So this would be T1 down here on the x-axis. T1. This would be T2. Whatever the time associated with that second concentration. We're gonna do a couple from problem number 2, chapter 4, okay? So you can see how this thing works. and then I'm gonna let you finish it out. That's part of your laboratory assignment now for this coming Friday, okay? So we're gonna do a couple of them. It's probably gonna be 5 or 6 trapezoids total. We'll do a couple of them, and you can finish it out and get the residual area that we talked about on Friday also. And then you'll be done with that assignment, okay? And then the width of this trapezoid, I messed up right here. See, I put a T there, that should be a 2. So it's the average of those two concentrations. And then the width of the trapezoid is gonna be whatever the second time is minus this first one. So if this was 30 minutes for C2, and this was 15 minutes here, the width of that trapezoid would be 15, right? 15 minute units, right? So I'm just gonna say T2 minus T1. Okay. That's the way we get the area for a trapezoid. So in chapter number 4, I'm just gonna see if I can do a couple of the. By the way, wow. Thank you, I appreciate that. So in question number 2 from chapter 4 of your textbook, okay? You got some concentration time data, and it goes from 0.25 hours all the way out to 18 hours. We graph this in laboratory or whatever the case may be. So you can go back to the graph and do this exercise if you want. So we have some data. And so that first trapezoid, the time is 0.25 on the x-axis, 0.25. And what was C0? 8.4 or something like that? Look it up right quick, comes out. 8.4. So when we drew our best fit line, this C0 up here that we back extrapolated to was 8.4 milligrams per liter. Okay. So that was C0. This was C1. And we're just gonna do the first 2. Then I'm gonna let you finish the rest. So don't forget that first trapezoid. So you got to draw that first one. But in the data set, they don't have C0, so it's easy to forget. But if you miss, let's say from time 0, 0.25, if you miss that first trapezoid, you're gonna be losing a hell of a lot of area, aren't you? So don't ever forget the trapezoid that has a left side height of C0, okay? So that trapezoid here, okay, has an area of C0 plus C1. Let's put the actual concentration in there. So, you know, what was that? 8.21. No, that first one is 8.21. So C1 is 8.21. 8.21 milligrams per liter, right? So that first trapezoid has an area of 8.4 plus 8.21 milligrams per liter, okay, over 2, and the width of that trapezoid is 0.25 minus 0 hours, 0.25 hours, 0.25 hours. Now, I'm skimping on units, but you're not allowed to do that yet because you ain't quite as good as me yet. But the units are always going to be what's on the y-axis times what's on the x-axis. So for that first all of these trapezoids are going to have units of milligrams per liters times hours. It's just height times width are going to be units. Don't care what kind of data you're looking at. Just look at the units on the y-axis and what's on the x-axis. The total units are going to be height times width. So whatever this numerical value comes out to, it would be units of milligrams per liter times hours. Are we straight with that? It's just the height times width. So that's the first trapezoid. The second trapezoid, let me see what C2 actually is in that data set. 7.87. So this data right here is 7.87. So that second trapezoid, just connect the dots, okay? That second trapezoid is going to have an area of 8, I'm sorry, no, I'm right.
Excuse me, sir.
Yes, sir.
So, just for clarity, we only use the points on the line.
Yes, you actually connected the dots for the data point. Exactly right. That's right, you connecting the dots, okay, with a straight line. So you need to draw one continuous straight line to get KEL doing C0 like we learned how to do. But to get the individual trapezoids, all you need to do is look at the actual concentration. You don't even have to connect the dots. You just know that first one, the height on the left side is C0, the height on the right side. You don't have to actually draw these connected dots on your graph paper. But you do need to draw a continuous one straight line to get your best fit line, so you can get KEL to C0, like we learned how to do. Are we straight?
So if those points do not follow the line, we don't use them.
If they ain't on the line, these data points, you're gonna use all your data points for your trapezoids. So for instance, as an aside,
So you use
let's
each
hold
data
up,
point.
because you're younger than me and I'll forget again, okay? Let's say your data set look like this. You can obviously see all those points ain't gonna be on the line, right? But to get KEL, you're gonna still have to draw a best fit line. That ain't the best fit. To get the slope of that line, and you're gonna still have to get C0. But now when I connect the trapezoids, my actual trapezoid, you don't have to connect the trapezoid, you can visualize the connection. Here's my first trapezoid right here. My second trapezoid is right here. My third trapezoid is right here. My fourth one is right here. So my actual trapezoids, I use the data points, okay? You use the actual data points to get each individual trapezoid, okay? But that best fit line, you got to use to get KEL and C0. That C0 now is going to be the height of the left-hand side of that first trapezoid. So you got to have that C0. If you miss that, you're going to screw it up real bad. So that second trapezoid here, still going to get y'all out of there. I don't care what y'all do. 2, and now it has, now the time associated with it is 0.5 hours. Here, the time associated with the 7.87 is 0.5 hours. So it has a width of 0.5 minus 0.25, so its width is 0.25 hours also, okay? Times 0.25, okay? So I do the math, we know the unit is gonna be milligrams per liter times hour. That's the second trapezoid. See if you can do the rest, okay? So this point here, that next concentration, 7.87, is 7.23, so on and so forth. That's 7.23, but I'm not gonna do that one for you, okay? And then see if you can get the area for that trapezoid. That time down there is 7.23. That time is 1 hour. So this time right here is 1 hour. I know it's supposed to be a linear scale. It's not drawn scale, but it's at 1 hour. So the width of that third trapezoid is going to be 1 hour minus 0.5 hours. It's going to have a width of 0.5 hours. Everybody see what's going on? Okay, so you're gonna come all the way out here to this last one here. Remember we said we got that residual area that goes from CX, CX just means the last data point, and then the TX is just the last time point. All of this area out here we said the residual area, and that residual area, I just call it RA, we said it was equal to whatever that last concentration is divided by KEL. So you're gonna have to add that to the area for the rest of the trapezoids as well. And then if you do that, that'll give you the total area under the curve. So CX, so you won't say I told you. This, when you tell me what's going to be the value of CX in this problem, anybody's looking at that data set. What's the value of CX, the last concentration you've taken? Nobody's looking at the data set? The last CX is going to be 0.4, and you calculated KEL in the laboratory, so that'll give you the residual area. So you need to add that to the area for all of those trapezoids. That's going to give you the area in the curve by the trapezoidal method. Questions?
We'll be doing this in lab, right? Because we're not gonna have graph paper.
Say that again?
We'll be doing the trapezoidal method in lab, right?
In lab? No, you're doing it for lab.
For lab.
You're going to come there with it done.
Yes, it's gonna be done. That's what I mean.
Yes,
But,
okay.
I mean, for the testing purposes, how, will we just use the equation to find area underneath the curve?
Perhaps. I might say do it by trapezoidal method. But I'm just telling you there are 2 different ways to
So
do
we'll
it.
bring our graph paper to.
No, you don't bring in it. You need graph paper. Guess who supplies it? Because I've seen graph paper grow wings, feet, and start out in front of the class and end up way back there somewhere. No, you know, the only paper you need, if any, because they say you're going to have these little white papers now, I don't know, but is a scratch paper. And I've seen it do spontaneous evolution too. Grow wings, and feet, and walk from one side of the room to the other, you know. Yes, ma'am.
So Dr. Felder, how would the question be asked? 'Cause I know you're doing like going through all the trapezoids just to show us, so like how would the question be asked? Would it say from this heat concentration or that concentration?
It's the area under the curve from 0 to infinity. It's from 0 all the way out to infinity. It's the total area under the curve from 0 to infinity. But now if I just want the area under the curve from 0 to 0.5 hours, that would be less than the area under the curve from 0 to infinity. But certainly I could calculate from 0 to 0.5 hours, just add those three trapezoids together. If I want the area under the curve from 0 to 1 hour, then I just go with 0. But I'm telling you, to get the clearance, we need the dose divided by the area under the curve from 0 to infinity. Times 0 all the way out to infinity. Where infinity for our model here is 5 half-lives or longer. It ain't the second coming of Jesus, okay? If that drug has a half-life of 2 hours, then anything beyond 10 hours would be considered infinity for our purpose. But if the investigator actually took blood samples, if the half-life was 2 hours, and the investigator followed this drug for 20 hours, fine. We'd have to take the last concentration to get the residual area, and the last concentration would be at 20 hours. Yes?
Is it possible to find the area under the curve using integration from?
This equation C0. Don't ask me no more technical questions that concern calculus, because I know you're trying to embarrass me, but okay. You probably want calculus with. But this equation for area under the curve does come from integrating the differential equation between 0 and infinity. So this is the exact equation that's obtained by integration of the, yeah. Now, one other thing, I'm glad you asked that because it just brought another thing to mind. This calculation of area under the curve, C0 divided by KO, which is model dependent or independent? Independent. No, this is model dependent. This depends on it being this model right here. It's model dependent. Now that's the second time I asked you that today, and I told you on Friday, sports fans, don't break my heart. I mean, I just had this pacemaker implanted just several months ago. Don't go mess it up. I said, you know, the pacemaker, I'm just teasing. Okay. Okay. So this is a model dependent method. Of these two methods for calculating the area under the curve, okay, this is mathematically exact. You know, like I say, from integrating the differential equation between 0 and infinity or 0 and time or whatever. This method of trapezoid. And you come to the laboratory on Friday, and I say, okay, let me see your area under the curve by trapezoid method. You say, oh, I forgot it, I didn't do it.
-2.
-3.
From the 20, okay. I'm telling you in far enough in advance for you to do this. Okay, so of the two methods for calculating the area under the curve, the trapezoidal rule or the trapezoidal method would slightly overestimate this method. Because each one of those, and I'm gonna tell you why. Okay. Each trapezoid, let's just call this C1 and we'll call this C2. So this is just one of the trapezoids, okay? From the plasma concentration time data. Well, T1, T2. Well, we're making this roof line, a straight line, right? Because that's what a trapezoid is. But in actuality, we learned from our first laboratory that for first order data, we can make it look straight by plotting logarithms, or either plotting the concentration on semi-log paper. But the actual concentrations for first order processes are coming down like this. Remember, it's coming down in a curvilinear fashion. Remember, for first order, if we actually take first order data and we plot it on rectilinear paper, it's curved. Remember that was from okay, so each one of those individual trapezoids from the trapezoidal rule overestimates the actual area by this much. But the more trapezoids we use, the more we can minimize that error in the data. So this question comes up and I'm surprised you haven't asked it. Okay, Dr. And here I'm showing 1, 2, 3, 4, 5, 6. I don't know if the data set in problem number 2, chapter 4 is 6 or not, but I'm just trying to give you the concept so you can do it, okay? But one could ask the question, well, Dr. Felder, why do I need to use all of those trapezoids? Can't I just use from 0 to 0.5 hours, and then use 0.5 hours to 18 hours? That'd be 2 big trapezoids, right? Everybody see what I'm saying? I mean, I'm just saying 2. I can condense it to 3 trapezoids out of the 6 here. But when you do that, you increase this error here in that area. So I mean, you could visualize it if we wanted to. One big trapezoid from 0 to 18 hours, but TX is 18 hours in problem number 2, because that's the last time. Okay? One big trapezoid would look like this way. That's one big trapezoid, but that's gonna magnify that error even more. So use all of the trapezoids that the data will allow you to use, and then how to minimize the error that we get from this type of. You straight?
So the more trapezoids, the more precise.
You're gonna use all of it, that's right. The more trapezoids, the more precise and the more accurate. I think that's all I want to cover there. Questions? Y'all straight? Okay, so I'm expecting a better performance on exam 2. I mean, I put the 2s in your toolbox. I'm expecting a better performance from this group for exam 2. One compartment model. Okay. So on Wednesday, we either start on urinary excretion or perhaps, because I'm pretty much finished except I want to do urinary excretion for this. In other words, I want to look over here. We've been looking in here so far. I want to look over here, but I'm thinking that, I can put that off to Friday if you want to, then, or either I can start on this tomorrow, which we on exam 1, it's not going to be, I'm going to tell you straight out, it's not going to be any problem with urinary excretion, but I might have some questions, okay? The problem is going to concern the types of things we're doing in the laboratory with plasma data. But on one of these days, it might be better for Friday, maybe I should start urinary excretion tomorrow, and, I only have one lecture that I want to give on that. And then maybe we take Friday for a review.
Yes.
But that don't mean it's a free day. If I come in here and I only see 10 people, well, okay, maybe I'm like, oh, So maybe we can take Friday, I think, I'm gonna look at the lecture schedule again. And maybe we can review. When I say review, I don't do reviews that often, but when I do, I ain't coming in here to try to give you the test. The reviews that I do when I do them are student driven. I mean, if you have questions or problems or concerns, whatever the case may be, I can briefly tell you the type of things that we cover. You know how to calculate half-life and rate constants and C0 and A0 if the initial amount of drug, which is the same as the dose. You know how to calculate clearance, volumes of distribution, all that kind of stuff. If I give you the time, you know how to calculate the concentration. How do I know? Because we did that in the lab last week. We're going to do some more of that this week, okay? If I give you the concentration, you know how to calculate the time to reach that concentration. So these are things I'm going to be testing you on, seriously. So on Friday, let's think in terms of some type of review. Okay? Is that fair?
Yes, sir.
And then on Wednesday, I'll talk a little bit about, that's tomorrow, I'll talk a little bit more about the mathematics, since you like mathematics, and related to drug excretion in the urine, okay? By adding system, absorption, distribution, metabolism, excretion, which is usually urinary excretion. That's all I have. I kept my promise. So I'll see you guys tomorrow, okay?
So for the exam, it'll be one compartment model, pretty much any calculation that you've
Anything we've done, taught about concerning one compartment model is fair game. Anything, everything.
But the multiple choice, we will have the urinary
Concepts.
excretion concept.
Okay, 15 multiple choice items, 5 problems. One compartment model could be anywhere. I ain't gonna give y'all a test unless you got $50,000 and you can write the test. I told you what the test is gonna
I got 100 for you.
I tell you what